So I have a simulation that I would like to show you. This simulation is one that is possible for you to see on Blackboard, and I will try to point that out to you. It's a simulation in which you have various masses and various springs. And I'm going to enlarge this a bit and show that there are some aspects to this that you can look at. If you click on the button that says Show Help, you see that you've got a ruler that you can move around. You have a reference line that can be dragged around, and you can hang masses on these springs and watch the springs go up and down and pull the masses off, and the spring returns to its natural length. So what I would like to do is to hang some masses on these springs and figure out how would I determine what the spring constant is of this spring. This is a lab actually that you're going to do. So I'm going to enlarge this simulation, and I'm going to try to shift things around and examine some things about this first spring. So I'm going to move this line so that it marks an equilibrium position of spring number 1. And I'm going to shift this ruler down here so that the 0 point of that ruler exactly lines up with that reference line. And now I want to hang various masses from this spring. I'm going to start with a 50-gram mass. And when I hang this 50-gram mass from the spring, we can see that the mass comes down to a certain point. And I want to make a table that shows what is the amount that the spring is stretched as a function of the amount of weight that's being hung from the spring. So I'm going to drag this line down here and see that it looks to me like this spring stretches approximately 1, 2, 3, 4, 5 centimeters when I hang 50 grams from it. So I'm going to make a recording of that. I'm going to make a table here of the amount of elongation as a function of the amount of mass that's hung from the spring. First, I'll notice that when there was no mass on the spring at all, the spring had 0 elongation, and that's the first data point that I've recorded. Now, when I hang the 50-gram mass there, I see that there's a 5 centimeter elongation. And I want to convert these masses into weights. So 50 grams is 0.05 kilograms, and the weight that's hung from the spring is 0.5 newtons. I'm going to record that in my data table. All right, now I'm going to take the 50-gram mass off, and I'm going to hang the 100-gram mass from it. And I'm going to pull this line down to the spring, and it looks to me like that the amount of elongation here for the 100-gram mass is 10 centimeters. So I'm going to record that in my data table. Alright, so now I'm going to remove the 100-gram mass, and I'm going to add the 250-gram mass, and I'm going to let it stretch here. Let me stop it from vibrating here. And let me pull down my reference line, and it looks to me like that the mass stretches the spring by amount of 25 centimeters, or 0.25 meters. So I'm going to add that to my data table. Let me pull this screen down a little bit so I can add that point. And now I'm going to remove the 250-gram mass from this spring. And we're going to go back and work with the data in this table. Now, for reasons that are going to become clear a little bit later, we want to make a graph of these data. The thing we controlled was the weight on the spring, and the amount of elongation is what responded to it. But we actually are going to want to make a graph of the force versus the amount of elongation. Now I'm going to graph this by hand. I have to make some choices. One thing the computer does when you use Excel is it makes those choices for you. But on the AP exam, you're not going to have Excel to help you. Sometimes the axis is already prepared for you, but it may not. So you have some decisions to make. I want to plot the force as a function of elongation. And so I'm going to look at my force numbers and see that I go from 0 to 2.5 newtons. And I'm going to look at my elongation numbers and see I go from 0 to 0.25 meters. Here's the axes that I have to work with. I'm going to draw a couple of axes and then make some decisions about how to section it off. So I've chosen to scale my horizontal axis in terms of meters here, and now I've got to make decisions about my vertical axis. And there's a way that I could set things up. Let me go back up here and look at my data and draw a free body diagram of what's going on with the spring for a moment. Let's let that dot represent the end of the spring where I hang the weight. There are two forces acting. So we're concentrating on the forces that are acting on the weight that's hanging from the spring. So the earth is pulling that weight downward. The spring is trying to pull that weight upward. And what I claim is that when the weight is not vibrating, when the weight becomes stationary, that those two forces are in equilibrium with each other, so that the amount of force that the spring exerts upward is going to be equal to the weight downward. And that's the reason that I have put here on this axis the weight of the spring on the vertical axis. Now I want to plot some points. We have that when there is zero force on the spring, zero weight, that there is zero elongation. Let me plot that data point. I also know that when there is 0.5 newtons acting on the spring, there's an elongation of 0.05 meters. Let me put that on my graph. When there's 1 newton acting, then there's an elongation of 0.1 meters. And likewise, when there is a force of 2.5 newtons acting, then there's an elongation of 0.25 meters. Now again, I've plotted these points kind of funny because I've put my independent variable on the vertical axis and my dependent variable on the horizontal axis. But the reason I want to do this is because I want you to see that this graph makes a line. I could draw a line through those points. And since this is a line, I could use the slope-intercept form of an equation to figure out what the equation for that line is. I could pick 2 points on the line, figure out what the slope is, figure out what the intercept is, and then write the equation. So I'll pick a couple of points on the line. So maybe I'll pick this data point right here that's on the line, and maybe this data point right there, and try to figure out what the slope is. So I've picked 2 points, and I see the force points are 3.3 newtons and 0.2 newtons. So I would say that the slope is going to be the change in the vertical divided by the change in the horizontal. And now I'll put that into my calculator and figure out what the slope of the line is. I get that the slope of this line is equal to 10 newtons per meter. Now the equation for this line is going to be y equals mx plus b. Y happens to be force. X is going to be the amount of elongation. B, the intercept, looks like it's right there at the origin. So I could write this as the y variable, the force, is equal to the slope times the amount of elongation. What I hope you see is that's Hooke's law equation with a spring constant of 10 newtons per meter. In other words, the slope of this line is the spring constant for this graph. The spring constant is the slope of this line. The spring constant for this particular spring, the spring that we saw a while ago that we put the weights on, is 10 newtons per meter. What that means is that if I wanted to stretch this spring a total of 1 meter, I would have to exert a force of 10 newtons, hang a weight that's 1 kilogram essentially on it, if the spring in fact could stretch that long. Now this is an idealized sort of simulation. In real springs, what you'll find is that you'll have some data points that are a little above or a little bit below your best fit line, but if you're working with a spring that is in its elastic range, then you're going to get a roughly linear version of the force versus the elongation, and that will obey Hooke's law.